That's the computational powers for 3 symmetric algorithms. However, before that, we want to play around with electronic code book by using a ppm file. So we will go to the GitHub to download the ppm file. So we're going to have copy all this and then just download that. So I already have the GitHub link over here. So we're going to download all these files. It's a matter of just right clicking and then copy the link address and then filling it to Replit. So we're gonna paste that over here and I'm just gonna enter that and we'll download the rest of the files all over. And then we use ls-al to see all the files that we've downloaded right here. So what we are interested in is to take this tags.ppm file, which it contains 2 parts. It contains the metadata as well as the pixel data. What we are interested in is encrypting the pixel data, so we need to take out the metadata. By so doing, we will go over here and then we will take the first 3 lines coming from the up to the down, okay, and that will explain the purpose, and I'm going to paste that in here. So that's it. So basically we're creating that. So we'll be creating a tags file, and then what we just done is to extract the header of the ppm file from the image into a new file called a tags header, and then we will extract the pixel which we're interested in using to do the encryption. So copy all that and then gonna paste that as well. Okay, and then we gonna, that's now we have the pixel part which we have done. So we can go ahead to encrypt the we can even add time to it if you want to encrypt the pixel part of it. So we paste this over here and then I'm gonna encrypt the pixel part of it. Once we have encrypted that pixel part, if we do ls-al, we have all our files here. This is the inside file right here. So now that we've encrypted the pixel part, we can concatenate and put the file back together. So we're going to use cat file and then put it all together again. Okay, so we have it together and then do ls-al and then we get the file that we have done. So that's the tags ecmb.ppm, this very file which contains both the metadata where the metadata wasn't encrypted but only the pixel part of it was encrypted. And then we will go up here. The reason why we did this is that ppm headers contains the metadata that define the format of the image, like describing what the image is, but it doesn't form part of the pixel information. So if we make a mistake by encrypting together with the pixel data, it could distort the information that we want to encrypt, and therefore when we are done it may not conform to the ppm format, said that we will not be able to read it and it will not be compatible with ppm. So it's always better to take out the metadata before you can use that. That answers this part of it. So we'll go straight download the file. That's the ecm.ppm is over here, tags ecm.ppm, and then just choose download and then we download it onto our desktop. There are online tools that will enable you to get those files here. So this is the original file, and then basically after you've uploaded that file and then we will download that file, it gives us this file. So you can clearly see the original file is very clear, but the second file you can still find patterns in there. So the key to what is happening is that ECB will always doesn't use counter chaining, so you'll not see much difference in it once you do encryption with any blocks. All that is just to take the same block, same key, resulting in the same pattern. So it basically leads to patterns being identified, and that is the key, the vulnerability with ECB. So ECB is not something that is really encouraged to be used, and because of that we don't expect the computational power to be high. So let's go ahead and then download a couple of files from the internet using the wget function. So we copy that and then we come all over here to that, and then we're gonna paste all these files and then quit. Yes, and then there we are, we have all our files here. So let's go ahead, let's use time to actually look at how long it takes to basically compute that. So this basically is taking three values, and here we are. So after we take 20 mbps, we will do encryption with the DAS encrypt decrypt decrypt, but a couple of times take the mean value, do similar for triple DES, and then do similar for the AES electronic code book. That's the 20 mbps. Repeat that for 40 mbps. Also take the mean values for 60, similar, and then 80 we do the same thing, and then also for 100 do the same thing, and we're going to plot a graph with it, which I've already plotted. However, I'll show how the graph was plotted. So let's move on. Here we are with data that I've collected over a couple of times. So we have 20 mbps, that gives us this data, and then what we are seeing how the graph is very linear as well, but then the growth rate is very slow, extremely slow compared to the triple DES and that function. So what I do is that I have formulas in the Excel that I try compute the sum of whatever that I'm looking for, and then it computes to give you. Then I have a second sheet that takes up the mean values which are coming from this one. So it takes care of the mean values, as you can see, like this. So it picks out the mean values, and then just a matter of just highlighting that, then using the Alt F1 will basically plot a graph for you. Then you can change the graph path, the graph type that you want. If you want it to be a line graph, you basically choose a line graph, and there you are. So you plot something similar to this, and then you just have to just label your axis very well, as we have here. So basically you compare this with the graph that you are seeing above, there isn't any much difference between these two graphs. So we have the file size which we have plotted from 20 to that, and then we have the timestamp. So we are looking at the runtime graph for 3 symmetric encryption algorithm, the EDE, the triple DES, and that. And then what we are seeing is that the triple DES EDE basically is a linear graph. It increases linearly, but it's quite sharp. And then compared to the code book, electronic code book, is not as so. But what is key to them is that as the size of the packet basically increases, you will find that the computational time basically increases for all the symmetric algorithms. So thank you so much for being in the class. It's been a great time. Enjoy your day. Bye. Thank you.